Hey everybody, this is chapter 13, trigonometry. If you've never heard of this topic before, we can just analyze the word really quickly. The first half of it, trigon, that basically comes from the Greek name for a triangle. You can see there it's a three-sided polygon, and metry it means measurement. So we're doing something with measuring triangles. So that's what this chapter is about, triangles, specifically right triangles. Later on, when we get to chapter 21, we'll go into the topic of trigonometry much more in depth. But for right now, it's just giving us some more techniques that we can use to solve problems with right triangles. So previously, we've studied the Pythagorean theorem, so don't forget that. We'll be using that here as well. But now we're going to have some more tools at our disposal to be able to solve some more challenging problems. So let's begin. This video is just about section A. However, I'm going to add a little bit to it at the end. So it's going to be A+. Maybe it's not your grade, but it is what I'm calling this video. And, you know, hopefully it can be your grade someday. Anyway, so right triangles that we're talking about, right? And we have a name for the longest side of a right triangle, this side here, right? It's the hypotenuse. We already know that. Now we're going to get a little more in depth. Previously, we just called the other two sides the legs, or maybe just the sides. But with trigonometry, we're going to pay special attention to a particular angle. And in trigonometry, we tend to use this symbol, which is the Greek letter theta. If you want to pretend that it's an x, then all the math is going to be the same. So if it makes you more comfortable, just use an x. But for historical purposes, we tend to use theta when we're dealing with trigonometry. Now, if we put that theta into a triangle in a particular spot, we're going to put theta right there. Then the two legs are now, we can differentiate between them. One leg is the opposite side of the triangle from that angle. You could see here in the picture, we're drawing an arrow from that angle all the way to the other side. So this side is opposite of our angle theta, and the other side is adjacent to it. And the word adjacent just means next to, and that side literally is next to that angle. If we put theta up here, so I'll call that angle x, then now the blue side would be the opposite with respect to x, whereas the green side would be the adjacent with respect to x. The hypotenuse, of course, stays the same. And for reasons that will become obvious in a moment, we're not going to consider the right angle. Right angles are kind of special, so we're only dealing with the other two angles of our triangle. So our textbook thinks that you've seen this before. Maybe you have, maybe you haven't. Regardless, what we're going to do now is define three ratios based upon those various sides that we saw in the triangle. The first one is called sine. The sine of angle theta is equal to the opposite side's length divided by the hypotenuse length. Okay, so we're taking a ratio of two side lengths of the triangle. The cosine of that angle theta is equal to the adjacent length divided by the hypotenuse, and the tangent of the angle is equal to the opposite length divided by the adjacent length. We could flip these ratios over and do hypotenuse over opposite, hypotenuse over adjacent, adjacent over opposite. Those would give us different ratios. They have their own special names. You can study those in a future math course. For our course, we're just going to deal with these three. It's really important that you memorize what these three ratios are. So when I was in high school, I just memorized this word up here, SOHCAHTOA, and that tells us sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tangent is equal to opposite over adjacent. That was enough for me. There's also various like sentences that you can memorize. So like down here at the bottom, sentence 5 and 6 just say SOHCAHTOA, where the first letter of each word spells out SOHCAHTOA. So you could memorize either of those two sentences. The last one's kind of funny. Sentences 1 and 4 are just sentences that tell us in a different order. They do tangent, then the first one's tangent, then sine, then cosine, and this one's tangent, then cosine, then sine. And then 2 and 3, they don't tell you sine, cosine, tangent, but they do tell you the ratios. We see like opposite hypotenuse, adjacent, hypotenuse, opposite, adjacent. So if you remember the order of sine, cosine, tangent, then you're good with those. Anyway, there's lots of ways. Just find a way that works for you. Now we know the triangles can be rotated and flipped around and stuff, so it's important that when we look at any triangle, no matter how it's situated on the page, we need to be able to identify where's the hypotenuse and then what sides are opposite and adjacent to what angles. So let's look at this one here. What is the name of the hypotenuse? The hypotenuse is going to be labeled AC, right? That's clearly the side that is across from the right angle or opposite of the right angle. What is the side that is opposite of, that's a Greek letter right there, it's alpha. Well, opposite of alpha is going to be right over there, so that makes that AB. And if that's the side that's opposite to alpha, then BC is going to be the side that is adjacent to alpha, right? That's literally right next to the angle. Opposite of, that's another Greek letter, beta. Well, opposite of beta is going to be over here. That's BC. And then adjacent to beta is going to be AB. What you'll notice is that the opposite and the adjacent switch when we change the angle, right? So opposite of alpha is adjacent to beta. Adjacent to alpha is opposite to beta. That's always going to be true. Next, can we come up with trig ratios for a given triangle? So we've got our angle theta is there. So sine of theta is going to be the opposite side divided by the hypotenuse. Opposite of theta is going to be y, and the hypotenuse is definitely x. Cosine of theta, the adjacent side to theta is going to be z or z. The hypotenuse is still x. And tangent of theta, we have opposite over adjacent. Our second angle in this triangle is another Greek letter. That's the Greek letter phi. Sine of phi is going to be opposite from phi, which is z, divided by the hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. So again, you can see that the sine of theta is the same as the cosine of phi. The cosine of theta is equal to the sine of phi. And the tangent of theta is the reciprocal of the tangent of phi. Those are not coincidences. That will be true in every single right triangle. And you can see, by the way, why we don't want to consider a right angle as our theta. Because if we did, well, the hypotenuse would still be the hypotenuse. But then how would we choose which one of these sides to be adjacent and which side to be opposite? Really, neither of them are opposite. They're both adjacent. It's actually the hypotenuse itself that is opposite. So none of the ratios make sense if we consider the right triangle, the right angle as our theta. Now the whole purpose of this is that we can use this to find unknown side lengths when the Pythagorean theorem won't do the job. So the idea is we're going to have a picture of a right triangle, and we're going to be able to identify in that picture some angle, and then based on that we'll have an opposite and adjacent sides, and of course a hypotenuse since it's a right triangle. We're going to choose an appropriate trig ratio. I think that'll be more obvious when we see an example. And then we're going to write an equation based on this. And then we're going to solve the equation. So let's take a look at one, or two actually. So both of these examples have right triangles, and both of them want us to solve for a missing side. But because we don't know the third side, we cannot use the Pythagorean theorem. But we can use trigonometry. So we look at this first one. We've got an angle given to us. It's 61 degrees. The two side lengths in the picture are, well, 9.6 is the hypotenuse, and x is the opposite. So we'd ask ourselves, what trig ratio uses the opposite and hypotenuse? Well, it would be the sine ratio. So we could write an equation right here. It says sine of 61 degrees equals x divided by 9.6. And then we want to get x alone. So x must be equal to sine of 61 degrees times 9.6. And then if we only knew what sine of 61 degrees meant, we could multiply it by 9.6 and get an answer. And that's exactly what we'll do on a calculator. This is really easy to do. We're just going to access the trig button, which is right here next to the 7. Click that, and we see sine, cosine, and tangent. These 3 we're going to talk about in just a minute. And these 6 we're going to talk about in future math courses. So in this problem, we wanted sine of 61 times 9.6. And the problem, in the book, they rounded this answer to 8.40. Okay? And this will all work, by the way, as long as in the top right-hand corner you see DEG. It's possible that your calculator may say RAD. If it does, then you're going to get a totally different answer, and one that's obviously very wrong since the side length could not possibly be negative. You can switch between these 2 settings by just clicking. If you're moving your mouse up there and clicking and it's not changing, that means that you have an older operating system installed in your calculator, and you need to fix that. If you bring your calculator to me, I can do it in a matter of minutes. As for what an RAD, or radian as we see the word here, is, that's something we'll cover later on in the course. So in the second example, we've got a right triangle. Our angle is 41 degrees. Here we have the opposite side is 7.8, and the adjacent side is x. So we're not going to use the hypotenuse in this one. Opposite and adjacent tells us that we should be using tangent for our work. So we set up the equation. Tangent of 41 degrees is equal to 7.8 divided by x, opposite over adjacent. And then we just get x alone. And again, we just go to the calculator and we'll do 7.8 divided by tangent of 41 degrees, and we'll get an answer. As far as finding sides is concerned, that's as hard as it gets. Look at your picture, figure out what trigonometric ratio you could set up, write an equation, get the variable alone, solve it using a calculator. That's all there is to it. 2 things I do want to add before I move on. First, since we know that the 3 angles of a triangle have to add up to 180 degrees, right? We could say in this first example, that could have been 29 degrees there, right? And then instead of using sine, we could have used cosine. And if we solve that equation, we'll get, this is our answer, 9.6 times the cosine of 29 degrees. But that's the exact same thing as 9.6 times the sine of 61 degrees, as we mentioned in a previous slide. Second thing I want to mention is that this is an exact answer. There's no rounding involved. It is 9.6, which is a number. It's an exact number, multiplied by cosine of 29, which is an exact number. When you go into your calculator and you type in cosine of 29, enter, you're getting a very long decimal approximation. That decimal does not end. The cosine of 29 degrees is irrational. So now we have new irrational numbers. Very exciting. Not all sine and cosine values are irrational. Most of them are. It'll be obvious when they are and when they aren't. Okay, when you type in sine of 30 degrees, for example, it's equal to 1/2. Clearly a rational number. There are some other trig values that you could experiment with on a calculator, and you'll find easy numbers coming out. But for the most part, you're going to get really long decimals. Those are all irrational. All right. So now let's move on to the next part, which is going to be finding missing angles rather than finding missing sides. So over here, we've got a picture of a right triangle, and we know 2 of the sides are 3 and 5. Hey, we could figure out that third side is going to be 4, right? Because that's a 3, 4, 5 right triangle. Wonderful. But what we're interested in is, what is this angle here? What is the value of theta? I know that's a right angle, but I don't know anything about this other side. So from the right triangle, we could set up this equation over here. The sine of theta is equal to 3/5. But we don't want to know what the sine of theta is. We want to know what theta is. Somehow we want to undo that sine function. Now, I say sine function because sine of an angle is not a number. It's not like we can just divide both sides of this equation by the magic letters sin and get theta alone. That's not how it works. We need to somehow undo the sine. just like if we had, say, x cubed equals 5, we need to get rid of the exponent. And the way we could do that is by raising both to the power of 1/3. And then the 1/3 and the 3 would cancel each other out. We need to figure out a way to cancel out the sine function itself. Now, we haven't spoken in this course yet about inverse functions, but we're going to use something here called the inverse sine. So for now, let's just agree that inverse kind of means the opposite. Okay, it means we're going to undo whatever comes after it. So inverse sine is going to undo sine, inverse cosine will undo cosine, and inverse tangent will undo tangent. Again, accessing the trig button next to the 7. Oh, it's right there, right below the sine. So we hit enter, and then we wanted 3/5. Again, we need to make sure that our calculator is set to degree mode, otherwise we'll get the wrong answer. But I'm in the right mode, so I press enter. There we go. My angle is about 36.9 degrees. So what we're going to say is that if this is true, sine of theta equals 3/5, then this is true also. And that says that theta by itself is equal to the inverse sine of 3/5. Let's talk about this notation really quickly. That is not an exponent of -1. We will never write an exponent of -1 over a trig function. Okay? If I wanted to use an exponent of -1, I would just write 1 over the sine of 3/5. Maybe you'd see sine of 3/5 all in parentheses raised to the -1. But when we see that -1 here, kind of next to the sine, in between the sine and the 3/5, I need you to interpret that as the inverse sine. And all that that means is it tells us the angle whose sine is equal to 3/5. And we can do this on the calculator. In fact, we saw it before. It's possible when you're doing these that you might get an error. So for example, something like this. What that generally means is that you used the reciprocal of the trig ratio. So in this case, it's not possible for me to have 5/3, because think about it. This is opposite over hypotenuse, and my hypotenuse could not be shorter than one of the legs. So if you get an error in your calculations, then just try taking the reciprocal of the angle of the side lengths. You probably just flip them around in your work by accident. Now I admit that it probably feels like I skipped on a little theory there. So maybe the explanation didn't seem as clear as it could have been, but that's because we really haven't talked about what an inverse means, and there's a lot left to be said there. But hopefully the process of what we're going to do here on the calculator is very straightforward, and I hope you understand that. So let's look at 2 examples here. We want to figure out this angle. So I look at the triangle. I've got opposite and adjacent, so that tells me we're going to use tangent. So I write tangent of theta is equal to 4/7. If I want to know what theta is, I go to my calculator, I access the inverse tangent, and then I put 4/7 in the parentheses, press enter, and I get my answer, 29.7 degrees. This one over here, my angle is down here in the bottom right. This empty side would be opposite, which means that I have adjacent and hypotenuse, so that means it's going to be cosine. Cosine of theta is 2.67/5.92. Great. Use your calculator, inverse cosine, get an answer. In the event that you happen to know all 3 sides of a triangle, or in the previous examples, if you just use the Pythagorean theorem to work out the 3rd side of those triangles, that just means that you have multiple options to use to figure out what theta is. So we know in this case that sine of theta is 4/5, cosine is 3/5, tangent is 4/3. That means that we could choose either to use inverse sine or inverse cosine or inverse tangent, and they're all going to get us the exact same answer. So that's the end of section A in the book, but we're going to add one additional thing to this. which is about triangle area. Now we all know that the area of a triangle is 1/2 the base times the height. Hopefully we all know that. But sometimes a triangle is, it's just not easy to work that out. So we're going to have a new formula for the area of a triangle that can be useful in certain situations. Now what I have here is a proof for the following formula, and this is the formula right here. If you're not interested in the proof, then skip ahead for a few seconds, but I wanted to go through the geometry of this one. So we're interested in the area of triangle ABC, so that's the large triangle at right, and we know that that should be 1/2 the base, which is AB, times the height, which is CN, and we're labeling that as AB is being labeled as little c, and CN is being labeled as little h. Okay, so we've got 1/2 CH is the total area. But if we consider this right triangle here, ACN, then we know that the sine of angle A must be equal to h divided by b, which means that we can rewrite this equation as h equals b times sine of A. And we can then put that back into this equation here, and we get 1/2 times c times b times sine of A. And then we just kind of rewrite that here as 1/2 bc sine of A, just to, I don't know, keep b and c in alphabetical order. Now that was going through this process by using this altitude, the height from angle C down to the bottom. But you know what? We could have done the exact same thing drawing in that altitude, or we could have drawn in the third altitude as well. So it's true that the area is equal to 1/2 times b times c times the sine of A. It's also true that it's equal to 1/2 AB times the sine of C, but then it's also true that it's equal to 1/2 AC times sine of B. What's important to notice about all three of these is that we have 1/2 times two side lengths, and then whatever two side lengths we're using, we then multiply by the angle that is in between those two sides. So using the formula in the blue box, area is 1/2 of A, which is this side, times B, which is this side, times the sine of C, which is that angle. Take a moment and make sure that you can see that with the other two formulas as well. Okay, now that was the proof for the acute triangle. You can go through a similar exercise here with an obtuse triangle. I'm not going to talk through this one, so just if you want to read through it, pause the video now and give it some thought. Okay, so let's look at an example of this. So here's a triangle. We want to know its area. It's really easy because look, I have a side and a second side and the angle in between them. So the area of this triangle is just 1/2 times 15 times 11 times the sine of 28 degrees. Go to your calculator. 38.7 is the area. So it's just a new formula, and it's very easy to use when you have the information that it requires. Notice in this triangle, if you tried to use 1/2 base times height, you would have to do quite a bit more work to figure that out. You'd first have to draw in a height, and then you'd have to look at this right triangle here and recognize that, well, the sine of 28 degrees is equal to the height divided by 11. Which means that you could rewrite that equation as h equals 11 times the 28 degrees, sine of 28 degrees, excuse me. And then we could go into 1/2 base times height. 1/2, the base is 15, the height is 11 times the sine of 28 degrees. But guess what? That's exactly what my formula said to do right away. So this is too much work. Just use the formula. All right, so that's all there is to basic trig. We should be able to find missing sides of a triangle if we know the angles. We should be able to find missing angles of a triangle if we know the sides. And we should be able to calculate the areas of certain triangles that used to be challenging, should now be easier with our new area formula. The rest of this chapter is just going to be applying these skills in various contexts. So we'll have a bunch of word problems. We're going to learn about bearings, which has to do with reading maps, and then we'll also apply this in 3 dimensions. So Let's get pumped.